Howdy, and welcome back to my introductory astronomy lecture series, Lecture 10, specifically for my class ASTR 103 Astronomy, spring of, that should say, 2022. I'm wondering if I should sit up doing these because right now I'm afraid that it looks like I have a huge stomach and a tiny, tiny head. Oh well, I'll figure that out later. This lecture will primarily be dealing with sibling worlds, the other three terrestrial planets, specifically Mercury, Venus, and Mars. But before we get into that, what I'd like to do is I'd like to finish up my discussion that I started in Lecture 9 with the home base, the Earth and the Moon. And so we're going to look at the Moon from an inside-out perspective, much like we did with the Earth. And what we find is, ironically enough, I start with the crust. Anyway, what we find is that the Moon is highly cratered. And that is the predominant geologic feature of the Moon, are craters and things resultant from craters. So we have the near side and the far side. Unlike what Pink Floyd would have us believe, there is no permanent dark side of the Moon, but there is a permanent near side and a permanent far side. Because of Earth's gravitational influence, it has locked the Moon into place. We refer to that as tidal locking, or in this particular case, synchronous rotation, meaning that the rotation of the Moon in a single day is equal to the revolution of the Moon around the Earth, or you could possibly think of that as the lunar year-ish, kind of. Anyway, what we notice is that from the near side and the far side, there is drastically different geologic features. Primarily, on the near side, we have maria, or mare, which is Latin for seas. These are large gray stains on the surface of the Moon. These are the geologic features you can actually see naked eye. So when you look at the Moon, I've heard tale of people seeing a person's face or a rabbit or what have you. Those dark stains are remnants of essentially lava flows. They are tied to cratering because what happened was that the impacts were large enough that they split the crust of the Moon open, and the liquid hot magma material from the mantle managed to seep up and then cover a very large plane of the Moon, eradicating all previous existence of surface features, cratering, and so forth. This happened very early on in the Moon's existence, during a time which we refer to as the late heavy bombardment era. When the solar system formed, you had the 8 major planets. They had accumulated their atmospheres, and you had a tremendous amount of debris just flying around. Again, apologies to asteroid commentary scientists. We had an order of magnitude more asteroids and comets than we do have today. And those objects had to go somewhere. And where they went towards any solid surface that would have them. And we see evidence of cratering on every solid world, be that the terrestrial planets, be that the moons of Jupiter, Saturn, Neptune, what have you. We see cratering everywhere. Now, what's peculiar about the Moon is that we don't really see anywhere else, is that we see these mare features because we believe that the gravitational influence of the Earth was strong enough during the formation of the Moon that it actually shifted the lunar core towards the Earth. And so the pressure and the thickness of the crust was thinner, pointed towards the Earth, than it was anywhere else. And so when these impacts occurred, it was able to break the surface of the lunar, break that crust, and then allow a very low viscosity lava to flow over hundreds or thousands of kilometers of area, again eradicating any previous history of geologic activity. On the far side, that wasn't the case, and so we have really no evidence of Mare at all, but we basically have a complete record of the cratering history of the moon. We do not find any evidence of major plate tectonics, primarily because the moon just wasn't geologically active for a long enough period of time. And I'll go into what I mean by timescales of geologic activity, what geologic activity is, and how we determine the timescales of when we refer to a moon or a world as either geologically active or geologically dead. The moon structure is similar to that of the Earth, although it is kind of a scaled, obviously a scaled down version of it. You have the crust, you have a silicate mantle, and then you have an inner and outer core. The outer core is molten, and then you have excuse me, I'm backing off that statement. You have a core, an outer core, then you have an inner core primarily composed of nickel and iron. We know these, and we know these this information from moonquakes. Same reason we know or have a good idea about the Earth is that when we sent the Apollo astronauts up there, we had them drop down a couple of seismographs, and we use those to monitor moonquakes, which do still happen. They're very minor, but they do still happen, and primarily due to gravitational stressing or tidal stressing. But they do happen, and we're able to use that information to model out what the interior of the moon looks like. And so when we look at the comparing the moon and the Earth's interior, we have an inner solid core, mostly of iron, and an outer molten outer core, again mostly of iron with some nickel thrown in there. The size of the core is, for the moon, is actually relatively small in comparison to the size of the core with the Earth. It's only about 20% of the radius of the total radius of the moon. There is, when we talk about the Dynamo Effect, what I'm referring to is the effect of a dynamo which creates a magnetic field. And for the Earth, again, relatively speaking to the terrestrial planets, we have a strong magnetic field because of a strong dynamo action. The moon, on the other hand, not so much. The moon has a very weak magnetic field. Most of it is frozen, meaning that there was a much stronger magnetic field early in the moon's history when the moon was actually spinning at a faster rate. And that magnetic field got frozen into ferromagnetic rocks. Now, the primary difference between the Earth and the moon is the rotational speed. And we'll revisit this again when I talk about Venus. One of the ways, or one of the crucial elements for creating a high magnetic dynamo is you have to get that material which creates the dynamo moving rapidly. And so for the Earth, we have a 24-hour day. That is fairly rapid in terms of this type of action. The moon rotates once every 27.3 days, or once every month. Venus has a far larger rotation period, and so that also has a much weaker magnetic field. But I'm getting ahead of myself. Mantle is semi-fluid rock, both in the Earth and the Moon, and we have essentially tectonics, or we have plate tectonics, we have volcanism on the Earth because, again, the Earth is geologically active. I'll just, spoiler alert, geologically active means that we have basically volcanic activity, ongoing volcanic activity. We have a mantle which is creating enough temperature and pressure to actually continue to break through the crust of the world and actively resurface that world through volcanism. Now, the Earth also has the added bonus of having tectonic plates because its lithosphere is thin enough that mantle convective action actually broke the the plates or the crust or lithosphere into plates, unlike, say, Venus. But for the moon, I wasn't sure where I was going with that final statement, but with the moon, again, we don't have any plate tectonics because the lithosphere was basically was too thick for the limited amount of time that the moon was geologically active for it to actually break that apart in any real way. There was volcanic activity very early on in the moon's history, but certainly nothing on that order now. Now, there are three hypotheses to where the moon came from. As I mentioned in the last lecture, the Earth-Moon system is fairly unique, and one of the reasons for that is, and a significant reason, is that the ratio of mass between the moon and the Earth is larger than in any other situation in the solar system. The moon is significantly larger, or the moon's mass is significantly more significant to the mass of its host planet than any other system. Like Ganymede's mass is nothing in comparison to Jupiter's mass. So the question becomes, how did it get there? We believe that the moons of Jupiter and moons of Saturn formed in sort of an analogous way of the solar system, where there was a disk of material. When the planet coalesced, there was still a disk of material surrounding it from which the moons coalesced. We do not believe that would be the case for Earth, because the Earth is not massive enough to really have a substantial disk from which a moon of this size could have formed. So there are a number of hypotheses bandied about. We have the capture hypothesis, the fission hypothesis, and the impact hypothesis. The impact hypothesis, as I will demonstrate, or as I'll talk about last, is the most generally accepted of the three. Oops. Got ahead of myself. The capture hypothesis, which I refer to as the sister hypothesis, is we believe, or it was believed, that the Earth and the Moon formed in separate parts of the solar disk, of the protoplanetary disk, and that the Moon got too close to the Earth and was gravitationally captured. It was very much like the potato moons of Mars were gravitationally captured when those initial asteroids came too close to Mars to do this. The problem with the capture theory is essentially twofold. One, it's dynamically unlikely. It's very unlikely that we would have something the size of the Moon get captured by something the size of the Earth. Earth is significantly larger than the Moon, but it's not that significantly larger. So more than likely, any sort of capture scenario is either going to result in the Moon just getting knocked in some other direction, or the Moon slamming into the Earth. The other problem comes in there are too many chemical similarities in the compositions. The composition of the Moon is very similar to the composition of the Earth's mantle. Obviously there are differences, but the similarities are far too large to be explainable by having the Moon form elsewhere in the solar disk and than the Earth. Then we have the fission hypothesis, or what I like to refer to as the mother hypothesis. In this case, you have the Earth is forming, and if you remember conservation of momentum, the Earth essentially is, when it's forming, it's shrinking, and as it does so, it spins up. And so the idea here is that part of the Earth spun away, or was thrown off of the surface because of basically just because of spin. Just threw off part of its material. And one of the arguments for this is the Pacific Basin is significantly smaller than the Atlantic Basin, say. And so it was hypothesized that the fission, or the fission part, came off the Earth. Problem with this is, again, a one of dynamics, but more importantly, one of composition, but in the reverse. When this happens, then if this were to happen, this would have happened prior to significant differentiation of the Earth. So the chemical composition of the Earth and the resultant fission body would be pretty homogeneous. And so what we find is that, or what we would expect, is that the moon would have a much higher iron and nickel concentration than it does now. So essentially, the composition of the moon is not as great as you would expect from the fission hypothesis. Which leads us to the impact hypothesis, or as I like to call it, the redneck hypothesis, where it's a merger between the capture and the fission hypothesis. So basically what we have is we have a case where a planetesimal, roughly the size of Mars, smacks into the Earth at a very oblique angle, and instead of breaking the Earth into pieces, it smashes in the Earth, digs out some material. This material then flies off from the Earth, but not fast enough that it escapes the Earth's gravitational influence, and then forms something of a disk around the Earth, and then essentially that material coalesces into the moon. This allows for both the chemical similarities in the chemical the chemical composition and the difference. The difference would come from the fact that the impacting body formed elsewhere in the solar system, whereas and was probably a little bit more differentiated. And then the similarities would come from the fact that there were a great deal of mantle material going into the recoalescing of the moon after that impact occurred. Now let's talk about the Earth-Moon interaction. First, let's talk about the lunar tides. Now, obviously, hopefully, you've all experienced ocean tides at one point or another. These are a consequence of the moon's gravitational influence, and really more specifically, both the moon and the sun. But we'll get to what the sun does in a moment. Let's just concentrate on the moon. And so, what we have is, because of the moon's influence, we have high tides and low tides, or tidal bulges. High tides occur on the near side and the far side of the Earth, whereas low tides occur at the poles. You can think of this as gravity stretching out the Earth in the Earth-Moon direction. Hence why you have high tides at the top and then low tides at, say, the bottom of the planet. There are a couple of caveats to this, couple of caveats to this image. One is that friction is a thing, and so there is a frictional force between the Earth's surface and the water. And so instead of being in a direct line, the tidal bulges are actually slightly off-center, because the Earth drags those bulges a little bit to proceed or follow that direct line. So high tides occur. High tides will occur prior to the moon being directly overhead. Now, you might be asking, why is this bulgy shape rather than teardrop shape? If the moon is on one side, you can easily see why the water would be pulled over to the one side. But why is it being pulled over to the right side? There's obviously nothing there, so what's causing that? Here you have to think of this system as a system really in free fall. The best example I can give to you is take 3 balls attached via 2 springs. So you have ball, spring, and then ball. And you drop it in a gravitational field. Now, because gravity is distance dependent, the gravitational attraction on the smaller sphere will be larger than the gravitational attraction on the middle sphere, which will be larger than the gravitational attraction on the top sphere. So the bottom sphere will move faster, the middle sphere will move middle-wise, and then the top sphere will move the slowest. And that stretches the whole thing. So if you're living on the top or on the middle ball, what you see or what you experience is that both the top ball, which is basically slower than you, is actually moving away from you, and the bottom ball, which is moving faster than you, is again also moving away from you. Think of the tides in that sense, where the Earth is the middle ball of that scenario, and the bulge closer to the Earth, or closer to the Moon, is the bottom ball, and the tides on the opposite side of the Earth are the top ball. So, because of this scenario, we on most locations will experience 2 tides, 2 high tides and 2 low tides per day. But, like I said, sun is also in the mix. The moon is not the only dominant, or the only thing throwing its weight around, as it were. Even though the sun is incredibly distant, it is massive enough that it still affects our ocean tides, in the sense that we have what are known as spring and neap tides. If you have an orientation where the Earth, Sun, and Moon are all in a line, where you would have it during a full moon and a new moon, respectively, then those 2 gravitational forces, or those 2 gravitational attractions, will sum. They will add up to each other, and so the tides will be exaggerated. So you have higher tides, and higher high tides, and lower low tides during the spring tides. In contrast to that, if you have a system where the sun, Earth, and Moon are at right angles to each other, as you would have during the quarter phases, first and third, then those 2 gravitational attractions will essentially not quite cancel out, but they'll work against each other. And these are referred to as neap tides. If the gravitational influence was exactly the same, then they would cancel each other out. But the sun's influence is significantly smaller than the moon. So what you have is just a dulling of the tides. The high tides are not as high, the low tides are not as low, and so those are referred to as neap tides. As you would expect to experience a high tide and a low tide twice a day, you will expect to feel a spring tide and a neap tide twice a month, as the moon goes around in its orbit. Once during full moon. Spring is once during full moon, once during new moon. Neaps are once during first quarter and once during third quarter. The other effect, and this more rapidly or more readily describes that preceding effect, where again you have a tidal bulge which actually is not in line with the Earth and the Moon because of the fact that friction is a thing. So what this means is that the moon and the Earth's rotation have created a lever arm. And so when the moon is acting gravitationally on the Earth, it's basically pulling more on the tidal bulge. Its influence, its gravitational strength, is higher at the tidal bulge than it is anywhere else. So it yanks on that arm. And what that does is it causes 2 things. One, it slows the rate of rotation of the Earth, because hopefully you can see that the Earth's rotation, as seen in this, is counterclockwise, whereas a torque, or a force acting on the tidal bulge, is pulling it in the other direction, as a force really acting in a clockwise direction. So it slows the Earth down ever so slightly, or is constantly slowing the Earth ever so slightly. The other thing that it does is it opens the distance between the moon and the Earth. The moon is slowly, ever so slowly, receding away from the Earth. Ultimately, this will result in complete synchronization, total tidal locking, where both the Earth and the moon will present the same face to each other, and the moon will be slightly smaller because it'll be further away. In that case, which will happen many, many moons ago, see what I did there? Or many, many moons from now, if you want to see the moon, you will actually have to move around the Earth. You will actually have to do what you do something similar on the moon. If you want to see the moon, or if you want to see the Earth on the moon, you move anyway. You have to move around the moon. If you're sitting on the moon, if you're standing on the moon, the Earth will hang there in wherever part of the sky it's currently located. Ultimately, when it's completely synchronized, the same effect will be seen on the Earth. The moon will just hang into the sky at whatever phase or whatever position it happens to be at. So, but this is millions, if not billions, of years from now. So, not something to really worry about. Again, this is a illustration of synchronous rotation or tidal locking, where you have, say, a flag on the moon, and you can see as it goes through its revolution, in order to keep that flag pointed directly at the Earth, the moon has to rotate. So I've encountered some sort of misguided notions that the moon does not rotate at all, because you can see the same face. Actually, because you can see the same face, that is proof or evidence that the moon actually does rotate. Because if it didn't, then we would see different faces as the moon revolved around the Earth. So let's move on to those sibling worlds that I talked about at the very beginning of this lecture. Again, we'll return to comparative planetology. Again, this practice is the practice of comparing and contrasting different worlds to see if there are any patterns that repeat, or see if there are any similarities that can be explained via one particular physical mechanism, or differences that require multiple different mechanisms to be at play with these worlds, specifically in terms of their geology, their construction, their surface features, their internal construction, and so forth. And then we'll also talk about what factors will essentially determine whether or not a particular planet is habitable for life, at least cursory anyway. So we have 5 stages of terrestrial planetary formation. We have differentiation, which I've described before is a process via which more dense material flows towards the center of the Earth, leaving lighter materials or less dense materials near the center of it. And you have this protocore that forms in the Earth. As the Earth cools down, you have that and the Earth cools down because the heat which was created via essentially the shrinking of the Earth, the formation of the Earth, it flows out of the planet and actually begins to create a difference in a temperature differential, and so therefore also a density differential. And this is the point where during this cooling that you have the different formation of structures. You have the crust forming, you have the mantle forming, and then you have the core forming. Then you have cratering, and again, this is during the time of the heavy bombardment. The Earth is cool enough that the crust is substantial enough that that impacts will cause cratering rather than get absorbed by the magma surface. When it hits, as we see evidence of this on the moon, for example, we have magma flooding. We have the Earth's, or the crust of the planet will break open, and fairly low viscosity lava will upflow and then flow over the surface of the world. Now, depending on the other factors involved, the amount of magma flooding will be more or less significant, particularly in terms, as I've said, with the moon's sides, and comparing the moon with Mercury, for example. And then finally you get to weathering. Now, weathering is akin to erosion, where you have surface features that are eradicated via either continued volcanism, wind abrasion, or water erosion, or action of water or ice moving across a particular surface. And that will recreate the Earth's surface, or excuse me, recreate the world's surface. So you might be wondering why the Earth has relatively few examples of craters. Certainly not as many craters as there are on the Moon. And while we do have a thick atmosphere that protects us from smaller impactors, that still doesn't quite explain why there aren't larger evidence of larger craters, particularly from the early beginning, or from the early times during this period time of late bombardment. As it happens, those craters, when they were formed, and then over time they were eradicated because of, like I said, geologic weathering effects, water, wind, and volcanism. To give you a sense of scale, or the sort of the action at this point, the crater, the Chicxulub crater, that is the remnant of the asteroid that slammed into the Earth and caused the extinction of the dinosaurs, or we believe caused the extinction. The crater walls at our highest are about 3 meters in size. That is tremendously smaller than what that crater's depth was originally. Again, those after 63 million years, the crater walls have been essentially eradicated because of the effects I've mentioned. So, the 5 stages of planetary differentiation. Again, you have that the terrestrial planets condensed from the hotter inner portion of the protosolar disks. This was due to, first, electrostatic accretion or electrostatic collection or gathering by very fine dust grains. Then came the accretion via gravitational attraction between smaller rocks, essentially, which turned into planetesimals. And all this time, during this time of these constant, essentially, bombardments, these constant slamming of material into that planetesimal, helping it grow, all of this created heat energy, which was trapped in that rock. And so when the Earth finally coalesced out of this, it was very, very warm. It was, well, basically molten. And that allowed, and there was a particular amount of large amounts of silicate rocks and heavier elements created in this process because of these high temperatures. And there was really not a lot of gases or ices that were around, because these are more volatile elements and were essentially destroyed in this process. The gravity during this the process of growing into planetesimals, the gravitational attraction is essentially uniform. If you have a sufficient enough mass, anything is going to pull itself into a spherical shape. Now, the reason why asteroids look potatoey is because, and I'm hoping I'm making some particular person very hungry with that. The reason why they are potatoey is because they aren't massive enough, and so the structural integrity, as it were, of the asteroid dominates the structure of the object. The stresses between the various components that make up the asteroid are more significant than gravity trying to pull everything into a single point. But if you get massive enough, then that structural integrity breaks down and the gravity wins and creates a sphere. And again, finally, when this Earth is molten, or has been created into a sphere, like I said, it's primarily molten, and as it starts cooling off, you have as it's cooling, you have differentiation, which is occurring, and then it cools off enough that those elements essentially get trapped where they differentiated to. So hence why iron and nickel are near the bottom, or near the core, or constitute the core, and the lighter silicate materials are found increasingly in higher abundances as you increasingly go up. The 5 stages of planetary cooling. What we find is that, again, the primary method of heating was accretion and differentiation. Again, you have energy that's slammed, energy which was imparted into the Earth because of the violent smashing, technical term, smashing of rocks into each other. That kinetic energy was the kinetic energy of the motion of the two rocks slamming into each other turned into thermal energy. Then you had differentiation occurring. Now you have rocks basically sliding against each other when they're molten, and that creates friction. And then you have the frictional forces acting, again, get turned into thermal energy. When the differentiation stops, you have much less energy, or the amount of energy that the world has, the amount of energy that the world generates becomes significantly less, and so the world will cool. While it is true that there is additional gravitational compression, which changes gravitational potential energy, or the potential for something to fall down or into the center of a world, there is gravitational conversion of that potential into kinetic energy of motion, meaning that it's getting squished. Again, technical term. Some energy is provided to that because gravity never stops. It's always there. It's always going to be trying to compress the Earth. So you get a little bit of energy from that. You also get a little bit of energy from radioactive decay. Elements like uranium and plutonium. These are going to cause, they release a little bit of energy every time these elements decay. And so you have additional heating because of this. But primarily the planet is going to cool, because this heating is not enough to replace the amount of energy that dissipates off the surface of the world. And so the cooling time is dependent upon the surface area of the world, whereas the amount of energy that it has, essentially you can think of the heat reservoir of the world, is dependent on the volume. The larger the world is, the more heat energy that is trapped or produced in that world when it was generated, or when it formed and is now currently decaying. And then you have a lot more, but incidentally you also have a lot more surface area from which to radiate that heat away. Because, again, if it wasn't clear, thermodynamics is a thing where you have basically the first law of thermodynamics simply states that if you have a hot object next to a cold object, the hot object will get colder, the cold object will get warmer, until they actually come to the same temperature. That's what the Earth is trying to do to space. The temperature differential between the two of them is around 270 Kelvin. The Earth is trying to get to the temperature of space, and because space is ginormous in comparison to the Earth, the temperature of the space is like, I could really care less. It is warming, I guess, a little bit, but primarily it's the Earth trying to cool down to its temperature. Now, how do we measure this cooling time? And really, what we're talking about is really the age of geologic activity, because geologic activity stems from high temperatures. If you can have a molten active or a semi-fluid active mantle being driven by a molten core, then you can have things like volcanism happening, or potentially even, or you can also have tectonics happening. Maybe not plate tectonics, but you can have the crust of the planet stretching or squishing. So how do we determine this time? Or at least roughly speaking, how do we determine this time? And it's fairly straightforward in that you compare the volume of the planet, which is the heat reservoir, in comparison to the surface area of the planet, which is where the energy is being dissipated, or how the cooling is happening. And so the time scale is, again, the first order, is the volume of the sphere divided by the area of the sphere. And that ends up being just a function of r, or the radius of the planet, meaning that a larger planet is going to be geologically active for a longer time period than a smaller planet. Pretty simple, pretty straightforward. Obviously, reality is a lot messier than that, but that at least gets you the first ballpark as to why the Earth is geologically active, but Mars isn't. Why is that kind of answers the question, why don't we see volcanic activity on Mars anymore? We know that it has been there. We know that there's been geologic activity on Mars, but we haven't seen it we have no evidence of it happening for at least 1 billion years. So, why did it stop? Then you have Venus, which is a little bit weirder. We do see geologic activity on Venus, not so much with tectonics, although honestly it's hard to really tell this because it's very hard to actually see the surface of Venus. You have to use radar techniques to do that, but we do have evidence that volcanism is still ongoing on Venus, on the Venusian surface, not nearly as much on the Earth. And again, it's a little bit more complicated to explain why the difference is the case, but part of that reason is that Venus is slightly smaller than the Earth. They are of comparable sizes, but Venus is a touch bit smaller than the Earth, and so it has cooled just that much faster than the Earth has. Then you have, again, kind of going back to cratering and magma flowing, you have that magma flooding is, or not magma flowing, magma flooding is because of cratering action. Most of the cratering occurred about 4 billion years ago, during the era of heavy bombardment, when the planets essentially had established themselves, and the rest of the solar system, I guess, kind of got angry at that and just pelted the planets with rocks and ice balls. And then finally, the Earth, or the worlds, cooled enough that these impacts no longer were able to, when these impacts occurred, the crust thickened because it cooled, and so magma was not able to so easily escape from underneath when the lithosphere, the crust, was broken open by this. Then you have weathering. Weathering is, as I've described before, is the action of wind, water, and current volcanism blowing away or destroying stuff, surface features, mountains, destroying mountains, destroying really solid structures or rocks, turning them into sand, or creating canyons like the Grand Canyon. You have the Colorado River, which is for millions of years dug out essentially a trench, which is now very, very pretty to look at. So good on you, Colorado River. And then you have volcanism, which when big lava flows, it just destroys everything around it, unfortunately, including people, if they're unfortunate enough to live by them. But weirdly enough, volcanism can also actually create surface features. It actually can build up surface features. So the only thing, so weathering due to water, ice, and wind actually destroy stuff rather than build them up in any way. Cratering can also build build up surface features. So now let's talk about the surfaces and interiors of these worlds. Now, how do they compare to each other? Here is an example of the worlds to scale. So you have, again, Mercury on the left, Venus, Earth, and Mars. Venus looks the way that it does because that is a radar image from Magellan, if I'm not mistaken, although I'm sure there's been a more recent mission. But it's been mapped by an orbiter, which has sent radar pulses down to the surface, which have managed to puncture through the very, very dense atmosphere and actually hit the surface, bounce up, and we have a topographical read on it. And so you can see that there is a lot of those veins and those wider areas. Those are evidence of volcanic activity. So we do know that it is pretty active. The whole point of this slide, or the reason why I'm putting this together, is to show you the variations of the different worlds. Mercury and the Moon are pretty much identical. They just look like giant rocks that have a whole bunch of craters on them. But you can see that Mars, which is significantly larger than Mercury, it looks rather plain. which is significant in and upon itself because it doesn't show a lot of evidence for craters. And so we know that most of the cratering happened around 4.5 billion years ago. Something must have eradicated them, must have reshaped the surface of Mars during its lifetime since then. And there are a couple of very interesting other geographic features, primarily the Vallis Marineris and Olympus Mons, which I'll get into later on. And then, of course, you have the Earth. You have Venus, as I've described, and then you have the Earth with its continents, with its water. It's a very nice blue, perfect sphere, or perfect blue sphere in the universe. What we have is one of the other, as I've frequently mentioned, we have these craters on the surface. Again, during this time of heavy bombardment. But we also have these things called scarps, which I'm sure a geologist could tell me why they're called scarps. But scarps are giant cliffs, and we believe that these originated for a very rapid cooling event. So the Mercury was cooling, and then for a reason which we don't fully understand yet, the moon cooled off significantly and tried to get smaller. Gravity tried to pull it in even more. The heat was the heat is fighting against gravity to keep it bigger, I guess. I'm really having a hard time with my technical terms today. But ultimately, if an object is cooling off, it's going to shrink. And the rate of cooling is going to dictate the rate of collapse. If the rate of cooling increases, the rate of collapse gets larger. Now we're talking about a solid body. And what that means is that it's not going to compress uniformly, or it's not going to collapse uniformly, it's going to break. And so that is the formation of these scarps that we see. So the Mercury, unlike the other three planets, went through a period of rapid cooling, intermittent rapid cooling, and to form these particular features. Now, this is what the Venusian surface looks like. This is, as far as I know, the only actual image that we have of the Venusian surface. Again, remember the Magellan images of the entire world are radar pulses. They are a radar map. This is actually a photograph, and this was taken by I'm going to screw up the name. The Russian name for Venus, essentially, Venerius. Wow, I'm blanking on that. Anyway, it's the Russian probe. Yeah, I really should know that. Anyway, it is a Soviet, I should say, a Soviet probe that actually managed to survive. Venus is ironically named after the goddess of beauty, and there's really nothing beautiful about it. The atmosphere of Venus is exceedingly deadly. Not only do you have very, very high temperatures at the base of the atmosphere, you have exceedingly high winds at the top. You can have wind currents of hundreds of kilometers per hour. So it's hard to get, so it's dangerous to basically fall through that. And then you have lightning storms that are frequent in the basically at the lower base of those higher altitude winds. And then the fun part is that it has rain composed of sulfuric acid. And then, on top of all that, so the probe has to make it through very high winds, get buffeted by high winds, dodge lightning bolts, and then not get melted by sulfuric acid. And then when it hits the surface, it is now experiencing a air pressure, or surface pressure, 90 times the strength of the Earth. So this thing is getting crushed like a tin can. And this Soviet probe, whose name I still can't remember, lasted an hour. They actually managed to have a probe land on Venus and last an hour and take these images before it got crushed like a tin can, which I got to give it to the Soviets for that. You know what? I don't think I actually said anything about the surface when I did that. So what we find, the conclusions that we find with Venus's surface is, again, the lithosphere is thick enough that we do not, where we find no evidence of plate tectonics. Now, plate tectonics is different than tectonics in that plate tectonics means that the lithosphere crust has broken into separate pieces. We believe the evidence that we have so far is that the Venus's crust is all one piece. We find that the surface is barren, as you can see. It is the most desiccated of all of the worlds because it is under such high temperatures. The temperature of Venus is actually higher than the temperature of Mercury, which is significantly closer. The reason because the atmosphere of Venus is almost exclusively carbon dioxide, and so the greenhouse effect is just rampant there. The surface pressures also are so high because of the thickness of the atmosphere, or the weight of such an atmosphere. One of the things that we notice that's peculiar is that there is a marked lack of cratering on Venus. And again, this leads us to believe that there is still active volcanism going on the surface. Even stranger than that, the surface of Venus doesn't appear to be more than 100,000 years old, meaning that there was a worldwide cataclysmic event which resurfaced the entire Venusian, which repaved essentially the entire Venusian surface. Which again is very difficult to explain why there would be a worldwide catastrophic event such as that on Venus. Then we come to Mars's surface. Mars is, like I said, it's kind of intermittent between the size of the Earth and the size of Mercury, and that size is probably why we see it the way we do. It's larger than Mercury, meaning that it kept its heat long enough to significantly be geologically active over a significant time period. So we do see surface features like Vallis Marineris. We also see the huge volcano Olympus Mons on the surface, which if you took Olympus Mons and put it on the Earth, it would roughly be the size of Arizona. So we know that volcanism definitely played a huge part in the surface history of Mars. We also see evidence of large plains which were not created by magma flooding. We believe that they were actually caused by literal flooding. There was a large ocean in the northern hemisphere of Mars. But now all we see is this pinkish or this peachish reddish color. And the reason for that is that the reason why Mars is the red planet is because you're looking at a whole bunch of rust, iron oxide. There is a significant amount of iron oxide in the surface of Mars, and so, yeah, it's rusted. But the reason why we don't see anything more, and I'm probably jumping ahead in terms of talking about the atmosphere, the reason why we don't see anything more is because the Mars is small enough that the cooling time scale is more rapid. And so Mars became geologically dead faster. Approximately, we believe that it became dead and lost its atmosphere in or about the same time. And that was about 1 billion years ago. So there is some provocative thought that Mars was once a habitable world like the Earth, with a thick atmosphere, with oceans and so forth, and potentially hosted life. And now we have been sending probes out to see if we can find any kind of fossil record for that life, or even in remnants or bacterial or maybe even multicellular life that has actually been able to survive the harsh conditions of the Martian surface. As this lecture is getting a little long, I seem to be rambling more often than I'm not. I will kind of go through these quickly. Vallis Marineris is a huge canyon on the Martian surface. If you were to place it on the Earth, it would run from California to the eastern seaboard. It is gigantic. It is ginormous. It is roughly, at the deepest parts, it is around 20 kilometers in depth. So it's about 3 times as deep as the Grand Canyon. unlike the Grand Canyon, which I said is formed by water action, the Colorado River over millions of years digging into it, we do not see evidence of any sort of water action creating Vallis Marineris. There is essentially the crater walls there are 4 crater walls. There is no opening through which via which water could have come in. So the most likely explanation at this point is tectonics. The mantle action basically split open, or not split open, but stretched the Martian surface enough to create this this trench, but not enough, or at least the crust was thick enough that it didn't actually break open and cause magma flooding. So let's look at the terrestrial planet interiors. They're all pretty similar to each other. We have a crust, a mantle, and a core of some sort. So that tells us that there was a singular mechanism that created these worlds. So all of the worlds were created roughly in the same way, primarily through differentiation and cooling, that allowed a iron core in the center and a semi-fluid mantle and, say, a crust. One of the things I want to point out is Mercury. As you can see, the Mercury has a ginormous core in comparison to the rest of the sides. It is far larger in ratio than it is for the other two. This is the reason for that, or the suspected reason for that, is that when Mars was forming, it too was hit by a fairly large planetesimal, but unlike the Earth, where that material stayed within the gravitational sphere of influence of the Earth and coalesced into the Moon, with Mercury, it just flew off. It just left. And so it did so during a period after the Mercury was significantly differentiated. So there is evidence to suggest that Mercury was significantly larger at some stage of its history, and then a lot of the mantle and crust material got blown off before it could fully cement into a planet. And so here we have a more detailed picture of the Mercurian interior. Again, you have a crust, you have a mantle, you have a molten outer core and a solid inner one, which again is oversized for the size of the world. Another possibility than the one that I just detailed for why there is a larger inner core is that the planetesimal was that Mercury was smashed into by a planetesimal of significant iron concentration, and the whole thing managed to stay essentially intact, or as one body, and recoalesced into Mercury. Mercury has because Mercury's size is so small, it wasn't geologically active for very long, and so therefore it did not produce a huge magnetic field. And again, also because of the gravitational interaction with the Sun, because of tidal locking, the rotation of Mercury is very, very slow. It's about 55 days. Yes, 55 days. So it is very slow. Again, a rapid rotation is needed for a robust magnetic field. Mars. Again, we have a lack of current plate tectonics, we have a lack of volcanism, we have a lack of a strong magnetic field, which we believe means that the core has primarily solidified, because in this case, the Earth, or Mars, has a similar rotation period that of the Earth. So it's got the speed, it just don't got the molten material to actually spin up enough to create a magnetic field. But, as I mentioned before, Mars does have, or Mars was large enough to sustain its geologic activity long enough so that we can see features like the Vallis Marineris due to tectonic activity, and Olympus Mons and the Tharsis Bulge due to volcanic activity. So, again, This is the Tharsis Bolts. Primarily, this is the Olympus Mons. And again, Tharsis Bulge extends even further, and there are 3 other volcanoes, shield volcanoes, along the... basically, if you were to manage to go down and to the right, you would see 3 more volcanoes. Again, it's the largest volcano. Olympus Mons is the largest volcano in the solar system. It's roughly the size of Arizona. This volcanism also is the reason for the high carbon dioxide concentration on Mars. Next, we have Venus, and we have the inner core. Again, we have possibly a stellar inner core. The problem with our understanding of Venus is that we do not have, don't really have seismographs on it, and so that has, in comparison to Mars, the number of orbiters which have gone around it is fewer. So our understanding of the specific or the bulk characteristics of its mass and its radius are not nearly as high as, or not nearly as precise as we do on Mars. So its interior is far less understood. But we do expect Venus, because it is of the same, roughly the same size as the Earth, we do expect it to be to have retained the same amount of heat or a similar amount of heat during its formation. And as I've said, it is a geologically active world. And we can see this through various radar images where you can see obviously a volcano. You also see from that volcano evidence of magma flooding, creating these large basalt sort of ocean basins, or very large basalt basins similar to what we see on the moon. The rotation period on Venus, again, because Earth and Venus are of comparable size, we do expect that the core of some portion of the core is liquid. But Venus has a exceedingly slow rotation period. It is the slowest of the terrestrial planets at 243 days, which is actually longer than the orbital period of Venus. So a Venusian day is longer than a Venusian year. And so because of this our extraordinarily low rotation rate, that is the reason for a relatively slow magnetic dynamo. Lastly, I'll talk about the atmospheres. The atmosphere of Venus is similar to that of the atmosphere of the Earth, except for one thing: it does not have a stratosphere. Because there is not a significant amount of ozone in the atmosphere of Venus, there is no significant amount of UV absorption, and so you do not have the wacky temperature inversions that you get, which separate a troposphere from a stratosphere to a mesosphere to a thermosphere. Essentially, all you have is just a smooth transition. As you go on to higher and higher altitudes, you just simply have the temperature cooling until you get to the very top of the Venusian atmosphere, at which point you hit that thermosphere or ionosphere, and the temperature drastically increases with altitude. And I've already mentioned that the atmosphere of Venus is exceedingly dense and rains sulfuric acid and contains sulfur crystals. Venus, because Venus's atmosphere, because it is primarily carbon dioxide, it has a significant greenhouse effect, warming its surface over 200 degrees Celsius, and than it would be if it had no atmosphere whatsoever. Now, one of the leading hypotheses for why this is the case is that Venus, because it is slightly closer in to than Earth, its surface temperature primordial surface temperature was warmer than the Earth's. And so if there was any liquid water on the Earth, it evaporated quicker. And that was sufficient enough that the water did not have time to absorb carbon dioxide. Water is a tremendous carbon dioxide sink. It is one of the mechanisms by which the Earth regulates its own carbon dioxide mixture in the atmosphere. Because the liquid water either was never present or because it wasn't present long enough, the carbon dioxide of the atmosphere never went away. So in a sense, when we look at Venus, we're actually looking at a primordial Earth. Venus is essentially an Earth-like planet at the very early stages of the Earth's atmosphere, just not quite as extreme. Then you have the atmosphere of Mars, which again, before I said there was no stratosphere. That was a slip of the tongue. There is no mesosphere. There is a stratosphere, but there's no mesosphere. But ultimately, like I said, what you get is with Venus, you have no ozone, and so you have the temperature just slowly decreases with altitude, and then once you get to the upper part of the atmosphere, it quickly increases with altitude, based on the fact that the solar winds and solar energy are smacking into it without any sort of protection. The Martian atmosphere is primarily carbon dioxide, and it goes through. It is the most variable of all of the atmospheres of the terrestrial planets, in terms of composition. Depending on the season, so the Martian ice caps, which are primarily carbon dioxide, or dry ice, they're primarily carbon dioxide ice. One ice cap is larger than the other, and so when that larger ice cap melts or sublimates, then there is a significantly larger amount of CO2 in the atmosphere. Then in the opposite season, when that ice cap cools and the carbon dioxide becomes solid again, and the other ice cap is not large enough to basically compensate for it. So the atmosphere varies in pressure significantly depending on if you're in the summer or winter in the northern hemisphere, for example. You do have clouds, which is kind of weird. Again, some of them are water ice clouds, some of them are CO2 clouds. These are very thin, tenuous clouds. They're not big puffy clouds like you see on the Earth. And occasionally, even though the atmosphere is thin, you can still have large enough motion, basically winds, that you can have localized dust storms where you have a little bit of dust being picked up and whirled around into these dust devil type things. Or you can have fairly localized sandstorms or dust storms, or you can have global dust storms where the entire surface of Mars is actually covered in dust. Thin air, you have thin atmosphere on Mars because of the fact that you have if we remember from last lecture, you can have atmospheric escape. If the escape speed is low enough, or rather if the escape velocity of the gas is high enough, and it exceeds the escape velocity of the planet, it can fly out into space. Now, here again, Mars's size defeated it in a way. Because Mars's size is so much smaller than the Earth, its escape velocity is significantly smaller than the Earth. And so, even given possibly comparable temperatures, gases like oxygen and nitrogen could more easily escape, given, say, 1 billion years, and escape out into space, leaving behind a very thin veneer of carbon dioxide, which is primarily supplied from the ice caps. So, if you get any ideas, if Elon Musk happens to be watching this, if you get any ideas about terraforming Mars, it's going to have to be an ongoing process because of the fact that Mars is just inherently small. It cannot sustain an atmosphere as robust as the Earth without some constant mechanism keeping up the amount of gas surrounding it. Atmosphere on Mercury is exceedingly tenuous. It is about the same as the Moon, although it is much more negatively charged than the Moon because there is this action called sputtering. Because it is closer to the Sun, it receives a lot more solar radiation and cosmic rays per unit area. And these high energetic particles and light will smack into the dust surface and actually cause the atoms making up the surface to break apart, and electrons will fly off from the surface, leaving protons and neutrons behind. And those electrons will then get trapped some of those electrons will then get trapped by the gravitational influence of Mercury, creating a very, very tenuous electron dominated atmosphere. And then that's all she wrote for today. I hope I didn't spin through the last of this lecture, because I noticed I was getting again over an hour, so I hope I didn't move too quickly beyond this. Didn't move too quickly at the end of this lecture. I should also say that if there are anyone watching these lectures that is not my student, and you are curious about obtaining the PowerPoint slides upon which I base these lectures, feel free to contact me. My email is located in the channel description. So yeah, feel free to do that if you'd like to review these slides in more depth, because I know I kind of get talky and stuff. Anyway, next time we will move on and we will talk about, I believe we will be talking about Jupiter and Saturn, the gaseous worlds, if memory serves. And so with that, I will bid you adieu. I hope you have found this lecture to be educational, and certainly I hope you found it to be entertaining. So with that, I will sign off. Peace out.